Hello guys, I got a message from a student requested for giving the details of the Melilite group of minerals. So I decided to go through it and make this video for you. I found it very interesting. The Melilite group of minerals, they belong to the class of sorosilicates. And as you all are aware, the Si2O ratio over here is Si2O7 groups. The Melilite group of mineral, it is not a very commonly occurring mineral. This is found in the ultramafic igneous rocks and high grade contact metamorphic rocks. Okay, so let us begin. These are the group of calc silicate minerals commonly found in igneous and metamorphic rocks, and these metamorphic rocks have to be high temperature low pressure contact metamorphic rocks. This name has been derived from the word meli. Meli means honey, and lithos is the rock, and that is because of its honey yellow color. You can see here this mineral, honey yellow color, it is common and therefore it is called as melilite, and it crystallizes in the tetragonal system. Normally, it has two principal constituents, that is the end members. Two principal end members are there. These are the gehlenite and ackermanite. Okay, gehlenite and ackermanite. So the gehlenite, it has the chemical composition of Ca2Al2SiO7, while ackermanite, which is a more common melilite, it is Ca2MgSi2O7. And the general melilite word is used for the solid solution, which is CaNa2Mgfe2 plus AlSi3O7. Okay, so you have to remember these two names, ackermanite and gehlenite, and of these, ackermanite is a more commonly occurring melilite. Now let us look at the structure. This seems to be a very complex structure, but actually it is very easy to understand. And in the structure of melilite, we come across two tetrahedra. The MgO tetrahedra, so this is the T1, and the SiO4 tetrahedra. Before moving ahead, I'd like to just take a quick detour and discuss with you an important point here, that normally Mg and O, they are in octahedral coordination. Octahedral coordination, where the coordination number is 6. And why this octahedral coordination is there? Because the radius ratio Mg2 plus to O2 minus is approximately 0.464, and from 0.41 to 0.7 is the range for octahedral coordination. But sometimes the Mg and O association, it also occurs as distorted tetrahedra. Distorted tetrahedra in some minerals or in synthetic materials as well. But always remember that MgO tetrahedra will not be forming the building blocks of silicate minerals like the SiO4 tetrahedra. Okay. So in this case of melilites, we get two tetrahedra. The MgO tetrahedra, that is the T1, and the SiO4 tetrahedra, it is T2. Here, the Mg atoms in the tetrahedra of O atoms, they are all, it is located in the center here. And all these four oxygens of the MgO tetrahedra, they are shared by the adjacent SiO4 tetrahedra. I will discuss it in a bit in the next slide by drawing it. So what is happening? That Mg atoms of the tetrahedra of O atom, that is MgO tetrahedra, T1 tetrahedra, it is located in center, while all the four oxygens which are at the corners, they are shared by the adjacent SiO4 tetrahedra. Further, since it is a sorosilicate, then the SiO4 tetrahedra, they are linked together to form the Si2O7 groups, sorosilicates. Once the MgO and SiO4 tetrahedra are linked together, then they form a five-membered ring. So if you see here carefully, I am drawing it by red color. This is the five-membered ring. Can you see this pentagon over here? The five-membered ring. These five-membered rings, they are linked together to form sheets. And in that five-membered ring is located the calcium atom. This calcium atom is linked to the oxygen of all the tetrahedra together. So the sheets of melilites, that is five member sheets, they are linked by this calcium atom. Now let me show you what that all meant. It sounds very complicated when you speak it out, but once you draw it, let me draw for you the structure of acrylonite, which is a more commonly occurring melilite. So please pay attention over here. First of all, we have to draw magnesium in the uh, MgO tetrahedra. So first I draw magnesium and I link it to four oxygen which are in the corner. Okay. And then as I had said, that each of these four oxygen atoms, they are linked to the adjacent silica tetrahedra. So this is Si, O here, O here. And one more oxygen is there, which I'll be drawing by green color over here. This green color circle is one more oxygen attached to the apex of that silica tetrahedra. So this is one oxygen linked to the silica tetrahedra, another oxygen linked to the silica tetrahedra. Let me draw for you again. Then the next one is over here, silicon, oxygen, and then one more is here. Okay, so the oxygens of the MgO tetrahedra, they are all linked to the adjacent silica tetrahedra. Now let us link or pair the two silica tetrahedra to form the sorosilicate group, which will be here like this. This way. Then we have it here. Like this. Let me draw the central oxygen over here. Now, I hope you can now see that five-membered ring. See this. Can you see this five-membered ring? And in between, in this large space, sits the calcium. This calcium is then linked to all the oxygens. Okay, so this is how this calcium is linked to all the oxygens adjacent to it, and thus you can find these pentagonal structures, they are all held together by this calcium. So this is the general structure of acarbonite. So I hope you can draw it. Let us do it a real quick one. First draw this kind of squarish structure, then draw the silica tetrahedra triangles. Now, in this, you have got the pentagonal sheets, this one, and here make calcium sit, and then join it with the corners of MgO tetrahedra and all the oxygens of silica tetrahedra. See, you have got the structure of acarbonite. This is how it is done. Very easy to draw. Now let us look at the chemistry. The general formula, very difficult to remember, but yes, if you want to fetch marks, you can. That is CN and K2 Mg, Fe2, ferric, ferrous, iron, aluminium, silicon, Si3O7. As previously mentioned, ackermanite and gehlenite are two principal components, but iron-rich, that is iron-rich and sodic melilites have also been reported. It has been found that the congruent melting temperatures, I hope you all know what is congruent melting. Please go through it. Ackermanite congruent melting temperature is 1451 degrees Celsius. Gehlenite is at 1590 degrees Celsius. But its solid solution, that is when ackermanite is 72% and gehlenite is 28%, then that solid solution temperature is a minimum of 1385 degrees Celsius. It has been seen that ackermanite is unstable below 500 degrees Celsius, while gehlenite is unstable below 600 degrees Celsius in presence of the water vapor pressure range of 4.8 to 6.7 kilobar. And once melilite it alters, then the natural alteration product include garnet, calcite, vesuvianite, and diopside. And the last part is the paragenesis. As I have mentioned previously, that melilite occurs in high-grade contact metamorphic rocks and igneous rocks. So in the metamorphic rock, it is characteristic of high temperature mineral associations in thermally metamorphosed impure limestones. Okay. And ackermanites, this is a very important point for MCQs, that ackermanite is a critical index mineral of sanidinite facies. Sanidinite facies, this is high temperature, low pressure metamorphic facies. The prograde metamorphism of siliceous limestones and dolomites, it gives ackermanite. How? Diopside and calcium carbonate, they react together to give ackermanite. At higher temperature, this ackermanite becomes unstable in presence of calcite, that is the limestones, and then starts reacting with the carbonate to form mervinites. Okay, so you can see this reaction. Ackermanite, if you are a bit good at remembering things, then you can remember these formulae as well as the equation. Otherwise, simply write this, that ackermanite, it becomes unstable and reacts with carbonate to give us the mervinite. And in the highest grade thermal metamorphism of such rocks, ackermanite and spurite, they again give rise to, they react together and give rise to mervinite and larnite. You are aware that larnite, it belongs to the olivine group of minerals. It has also been seen that melilite is a common constituent of feldspathoidal rocks formed by reaction of basic magmas with carbonate rocks. While in the igneous rocks, it is a dominant constituent of plutonic ultramafic rocks. They have been named unconfagrite or pyroxene melilitolite and sometimes in carbonatites. Remember, when it is a plutonic rock, it is called as melilitolite. When it is an extrusive rock, it is melilitite. Okay, melilitite. In the extrusive rocks, the melilite bearing rocks or melilites, they contain melilite in ground mass and sometimes in the phenocryst. And it has also been reported in melilite leucites, melilite tuff, and with olivine and montelicites. In India, melilite has been reported from Deccan traps and from carbonatites in the Meghalaya. There are some reports of melilite occurring in Andhra Pradesh. In this lecture, what is more important is the structure, how you have to draw the structure of melilite and the paragenesis. Okay, so this was a quick lecture. Thank you for asking me this question. I would recommend all of you to keep sending me your requests for certain topics, which also help me to increase my information and knowledge about such topics. I really like mineralogy and always wish to discuss it with you. Send me more questions. Thank you very much. See you next time.